Alright, silly people, here's the situation. We're going to be making a code which does Gaussian elimination on matrices and can solve systems of equations, but in a little bit more of a complicated way. And that way is called LU decomposition. Um, Effectively, what it does, the linear equation is a times x equals v, and you're solving that equation. What the LU decomposition does is it turns A into a lower triangular matrix times an upper triangular matrix, L times U, and then it uses that to figure out what the solutions to V are. Um, and so it's actually pretty cool the way that it works, and I recommend you go and read the theory section about this in the book right before this problem. Um, but I'm going to get into actually doing it here. So this is like the base version of the code that Newman gives us. This is just Gauss-Elim.py, modified a little bit, you know, importing all of NumPy instead of just bits of it. And for right now, I'm just going to modify this so that it does LU decomposition instead of the regular Gaussian elimination process. So this part is called the back substitution again. This is what it's called in the theory. And that's one part of the problem. There's going to be a new part of the problem, which is called forward substitution, where we're going to figure out a vector y where that solves L dot y equals x, but we'll get into that in a second. And in this loop is where we're going to do all of the LU stuff. This is where it's all going to be defined. So first thing we want to do is actually define what L is going to be. It's going to start off as the identity matrix. So we're going to call it np.identity, where the arguments are just however many dimensions you're working with, so n is fine. And then I want it to be a float data type in there. You actually want your u to start off as an identical copy to a, and you do that by just setting it equal to a.copy. Whenever you get into your for loop in M, though, this is where you're going to start flipping stuff around a little bit, so we can actually get rid of these lines here. So immediately we're going to go into for I in range, and actually that whole thing is gone. It's just this loop that remains, but we can get rid of the contents here. So this time we're going to change u as we go. So first we have to figure out what a given factor is. This is like a00, and it's calculated by taking the element of u that you're on and dividing it by its diagonal element in the same column, right? Then you just make it so that your Li comma m element is equal to that factor. And then what you do is you take your whatever row you're on, so ui comma colon, and subtract off this factor times u indexed the row m, so the diagonal element that you're evaluating, but just times that whole row pretty much, right? So that's whenever it gets done running through that loop, it will correctly construct u and l. So we can go ahead and see what those look like. Before we do anything else, let's just comment the rest of this code out for now. And I'm going to introduce to you a really useful NumPy function that we haven't really done on the channel before. It's numpy.dot. What it does is it actually does matrix multiplication between different matrices. And so if the theory works, and it does, and we did the code right, whenever we print L, or it's np dot L comma U, it will return A, because L times U should be equal to A in the linear equation. So let's see what happens if we do that. And indeed, whenever we print that guy, we get a matrix that's identical to our input matrix A. So we did do that all correctly. And we can get into the forward substitution, back substitution bit of the code. So the forward substitution, you have to create a new vector called y. This is the one that's going to be solving the equation L dot y equals x. It's going to have the same size as x. It's also going to be a float array. You run over the values of n, and you just make it so that y indexed a is equal to, you make it equal to v indexed I minus numpy dot dot of L indexed, and it's capital L indexed I comma colon I, which means it's whatever row of L you're on, you're only going all the way up to the value right before the diagonal value in each of those rows, right? But then you dot that vector with y colon I for the same effect, just everything up to that particular I that you're on, right? And I should do I in range, not for I range. There we go. Then we can get back into the back substitution bit. This part of the code actually is going to stay the same. The only, or not exactly the same. We're going to get rid of the contents in here and do it a little bit more efficiently. I'm going to replace M with I so that I have, just a little bit of like solace from the fact that I is a better letter for iteration than M. But X indexed I is going to be Y indexed I minus numpy dot of U indexed I comma I plus 1 colon with X of I plus 1 colon divided by, and actually the whole thing is divided by U indexed I comma I. That's just solving the equation between x, y, and u. That's, again, given in the theory section of the book. I recommend you go reading that. But with that, if we print x, it should print the same solution set of this set of linear equations that we did without all of that LU nonsense, which it did, so we're good. The next part of the problem is to also implement the what's it called, partial pivoting into this as well, where that's whenever you have a leading element of a row below the diagonal element that you're working on. If that magnitude is greater than this one, then you flip the rows, and this is how you avoid dividing by 0 in certain cases. And we'll even make this value 0 to test it on. So to implement that in the code, what you want to do is you want to put another for loop before the for loop where you're changing the values of L and U. This for loop is going to be dedicated to figuring out what you need to change as you go. So this is another for I in range M plus 1 comma N. This is just going to be flipping rows. So if it happens that the absolute value of the element that you're on I comma m is greater than the absolute value of the diagonal element you're working on, so u m comma m. Then you want to go in here and you want to say you flip the elements of those rows, right? So create another for loop in here to run through all of the columns of said rows, and then just make it so that you're replacing u indexed mj and u indexed ij, set them equal to u indexed ij comma u indexed mj, right? Pretty cool. And you also need to do this for L, but you only need to do it on the columns that are less than the m that you're working on. So if you're doing if j less than m, then you do the same thing with L. You flip the rows. And so I'm just going to copy this line of code down here and make it so all of these are L's instead of U's, because it is just the same operation of switching rows. Okay, after the for loop, you can change the v vector as you go, and it's much the same. It's v indexed m comma v indexed I equals v indexed I comma v indexed m, just flipping the rows again. And then you proceed through the rest of the code. The defining of u and L happens, the forward substitution and the back substitution happens. Yeah, nothing else really changes. And if we run it, it does end up getting the same values for this system of equations we did in the last episode where we did the partial pivoting before. So it looks like it's working. So I think this is a really complicated thing for somebody to do on their own, especially considering like so many people have done it before. Linear algebra packages are standard with every computer language, I think. And so this is a cool exercise, but I really hope that your professor didn't assign this one, and I'm sorry if they did, because it's tough.